All right, let's go ahead and solve trapping rainwater today. It's a hard problem. I figured this out yesterday. It's, I don't know if to say like it's the hardest problem I've seen. It's really not. I haven't solved a lot of hard problems, but I saw a lot of comments and a lot of people saying this was one of the hardest problems they've encountered. I don't know if it's because of the problem I did before this one, which was container with most water, which is not the same, obviously, algorithm, but the same pattern, 2 pointers. At least, you know, there are multiple ways to solve every particular problem. But obviously, thinking about an efficiency, I think the 2-pointer approach would be the most efficient for this, just because we can do big of and time, and we can do big O of constant time for space. So in that case, I think the 2-pointer approach would be the best one to pick, but obviously, you know, it's all depending where you're getting asked this question and what's the follow-up and the approach your interviewer wants you to do or whatnot. I think the concept of this problem is, it's simple once you understand a few things. And I kind of like these problems because they apply to real life scenarios, if you will. Like, let's think about this problem. It says given n non-integer, it says given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. We have an example here that is this visualization we get, and it's basically, so the width, it's 1 for all of them, right? We don't have to worry about the width because it's going to be 1 for all of that. I think that's irrelevant to solve this problem. This is just basically telling you this is the elevation map. So we can see the first index is 0, so we don't have an elevation there. Second index is 1, we have an elevation, then the next one is 0, this one's 2, this one's 1, 0, and so forth, right? So the hard part to understand about this problem is that we need to know the state of the tracking we're doing at that particular point, and I'll explain that. So let's say we're going to start iterating here, right? We're going to start iterating over here. We already said we're going to do a 2-pointer approach, so we're going to start with left pointer here and the right pointer here. Now this is 2-pointer opposite ends. For multiple reasons, we have one input array, we have to find one particular solution, and basically the 2 points are going to scan inwards the inputs as we iterate over the board. How do we iterate over this? Well, the benefit of 2-pointer is that we can know what is happening until the point we are exploring. And what I mean by that is, if we move left to here, we know we have a way to know what happened before that because we already seen it, right? That's something that, at least to solve this problem, you should know at this point. Same thing with right. Like if right gets to this point, we should know what happened that way, right? We should track the information we need before that. So for that, what I mean by that is, when we're here in our iteration, right, the left pointer, we're going to start on this end. What do we have in both ends? So at this point, we don't know what's left to left, right? So there's really nothing we can compare. We can imagine there's nothing over here or a 0 over here because we don't know, right? So for that, we're just going to move left to the next one. We need to know what is happening in the board, and I'm going to get into the details. So we found the first point of elevation, right? Remember, we're looking at an elevation map. So we found the first point of elevation. And we say, well, what is to our left? Well, to our left there's nothing, right? We already said there's a gap there. There's nothing. Okay. And there's nothing to the left of that. So we're looking to trap water. Conceptually, the visualization helps because we can see when we can trap water, right? We can only trap water when we have enough elevation to trap water between them, right? Okay. Well, that makes sense. So we can technically think about this as walls, right? Because you can trap water between walls if whatever is laying between them, it's a gap, right? Thinking that this is a flat gap, right? This is just for the sake of the metaphor, but I mean, obviously, if you have a hole here, there's no water, it'll go down, whatever. We're not looking at the physics of this. We're just looking at the plain concept. So we already said, since we're looking at both ends and we need some sort of gap in between to have water trap, we realize that when we find an elevation point, we can't have water trap unless there's walls around the point we are, right? So we know there is a wall all the way to the right here, of height 1. We know that because we're right on top of it. And we know there's a wall here at left because we're right on top of it. So we know that those are the main points we're standing right now. Now, since we know that there's nothing to the left of it, at the point we're standing right now, there's a wall, and there's nothing to the right of it, then there's no possibility to trap water in there, right? Okay, that's implied, that's easy. Well, we move left to here now, right? It stays here. We move left to here, and look what happens. Well, we don't know yet that we have this wall here, right? We don't know that. We only know that we have a wall all the way here. We haven't checked this to know that there's a bigger wall in front of us. But we do know that there is a wall we just left behind, which is this one. What is the elevation at the point we're at right now? Well, there's no elevation, right? It's 0. Okay. So if I have a wall to my left, and I know all the way there's a wall, then I know I could have water where I'm at. Why? Well, I know there's an elevation of 1 here, and I know there's an elevation of 1 all the way here. That's enough for me to know that at this point right now, I could trap water. Now, how much water I can trap? Because at the end of the day, that's the answer we're looking for. How much units of water we can trap. So, well, I have a wall of height 1, okay, which is this one here. And I have a wall of height 1 all the way here. So I know that I can trap at least 1 unit of water. And that's my answer. There's no other elevation at the point I'm at right now. That's our left pointer. I know there's a wall all the way on the left out of elevation 1. And I know there's a wall all the way to the right of elevation 1. So I could trap water where I'm at elevation 1. So that's what we add to our output. We're going to have obviously an output array, an output integer that is going to be counting up how many units of water we trap. So for now, we found 1 unit of water we can trap. We know that. Great. Let's clear the board. Let's move our left pointer here, and let's keep our right pointer here. Well, what happened here is very interesting. We already have 1 unit of water here. Let's try to keep adding to that. But we have another scenario here where we're looking at a wall and it's of elevation 2. We know that we have a unit of water back here, and we know we have a wall that's smaller back here. So we just confirm, right? Leaving this behind, but we just confirm that evidently we could trap this water here because we just found a taller wall here. We didn't find another gap. If that would be a gap there, that means we could still trap water of height 1 as long as right is equal to 1, right? Because all that water will be contained at that level. Great. Let's just keep that in mind as we move forward. So now we found a wall of height 2. But we know all the way to the right, there's a wall height 1. Interesting. So now the smaller wall, it's to the right. So I know that I have a unit of water 1 here. And I think about, can I trap water at this point? Well, not really, because my wall right here is taller. So the water level, it's going to be limited, if you look at the graphic, by the smaller point, by the smaller wall. Why? Well, let's think about this. My right wall is 1, my left wall is 2. If I try to have 2 units of water all the way to the right, what's going to happen here? Well, it's going to spill, right? We're not looking at the physics of this, but we know that water is in liquid state and it cannot be contained if there's no point of stoppage right here, right? So we think, okay, what about if we decide to move right now, move the right pointer forward or closer to the left to see if maybe there's a bigger wall to contain more water, because at the end of the day we want to trap water in it. It doesn't say trapping the most water, but we want to know how much water can be trapped, and for that we have to think about trapping more water. We're not looking to get rid of water. We want to know how much water it's trapped between our walls. So at this point right here, I'm left standing at 2, a wall of height 2, and I look at my right and I say, well, I cannot trap any more water. I still trap in just 1 to my left. What about if I try to find a taller wall on my right? Because I know every water unit here would spill out, right? Because we already know, I mean, we have an array of length n. There's nothing to the right of right, or there's 0. So we're assuming that the length of the array is going to be defined to a point that it's n minus 1 and not infinity, okay? So with that out of the way, we're always going to know that we have 0 walls to the left of our left, to the right of our right, okay? So let's go ahead and think about moving right to a point where we're a little more hopeful, because we want to trap more water. So now we say, okay, let's move right. Since right is the smaller wall, let's go ahead and try to find a larger wall on the smaller wall side. So I have right here, and look what I found. Well, I found another wall of height 2. Great. Okay. So now I ask, how much water can I trap to my right? I left a wall of height 1 right here. Is there any water trapped back here? Because I already know there's a difference, right? I already found a taller wall, so I asked the same question I was asking here. How much water was trapped at this point? Well, like we said earlier, there's nothing here to contain that, and we know that. So there's no water trapped here because it would spill out to, the gap, the base. So with that out of the way, we say, well, cool. We already know that we can probably trap more water in all these points that we still have to examine. We know that in the visualization. Obviously, in the array, you can do a mental model and kind of see that you could. However, we're given instructions to our computer won't know that until we have a result, right? So at this point, we're going to try to keep looking inwards to see if we can trap water from the smaller point. Why? Because if everything after a smaller point would spill, like we said here, okay? So now we found 2 points that are equal. So there must be water between them, right? Now we know there's nothing to the right. They are equal. Okay. But let's go ahead and say, hey, now we know we have two taller walls here. There's nothing to the right of it. But let me just keep track of the tallest wall I found on my right. And I'm going to just do tallest. Right? It's going to be equal to 2. Because I want to keep that in mind. I want to know how high my wall is on the right. So I know every time I move, every time I check a new point, if I can compare with that point and say, hey, could be water. There's any water that could be contained here based on the height of that wall I just left. Well, that's a good thing to keep in mind. We're going to do the same thing on tallest left. We just want to know how tall the wall is, how high. What's the height of the wall? That's what I'm trying to say. So at this point here, we found two equal walls. I mean, honestly, we can move any point because they're the same height. So we're just gonna get hopeful and try to find the smaller point, so we know if there's a gap, we can trap water. And we're gonna do that this way. I don't want to delete all this stuff. Oops. Great. So at this point, we already know it doesn't matter what we move. Put a T there. It doesn't matter what we move. They're the same, right? Let's go ahead and move right because we're already checking on right. We have some data on left. Let's go ahead and move right. They're equal height, so it really doesn't matter which one we move. We're just going to assume that we're going to find a smaller wall so we can trap water in it. And that's exactly what happens when we move right one more point to the left. So we move right up here. We know there's a wall of height 2 on our right that we just left behind. It's right here. We saved it. We are keeping track of that state. And look what we found here. Well, we found another wall of height 1. Cool. Okay. So we have a wall of height 1 here, and we have a wall of height 2 all the way down here. So what is the height of my tallest wall to the right? It's 2. And to my right is 2. But I found a wall here of height 1. Interesting. So that wall is of height 1, but my tallest walls are of height 2. So there must be at least 1 unit of water on top of me because I have tallest walls surrounding me. I know that. So I know there's a tallest wall right here and there's a tallest wall right here. Even though I found another wall of height 1, I have another unit I can go up to store water, right? So basically, this is the other point right here we got to keep in mind is the fact that the water level is going to be equal to the minimum height, which at this point it's 2, right? We're going to do minimum height minus the actual height. So what I mean by that is, well, the minimum height right now is 2, right? And the actual height I have right now is 1. That's the height I found. So 2 minus 1 equals 1, meaning I can trap a unit of water right above my height because I have 2 walls that can contain that, right? And like I said earlier, we don't know what's happening in between us, but what we know so far, it's enough for us to calculate the rest, at least at the point we are at right now. Perfect. So knowing that, we go ahead and add our unit of water to our answer. We found another unit of water on the right. Great. Our right pointer is standing right here. So we asked the same question we asked earlier. We have a wall of height 2 here. We have a wall of height 1 here. We know there's a unit of water. So knowing that, I have a wall of height 2 over here. So knowing that, okay, can I find a tallest wall? Or can I find a lower point? So if I find a tallest wall on my right, then I want to go and check what's going on the left. Because again, we're looking to contain things between them. If I don't find a talus wall on my left, then that means the right is going to contain water. And what I mean by that is when we move our pointer to here, we can immediately see that the heights are again equal. Okay, so they're equal. I just left a unit of water behind. I know the talus wall back here, it's also 2. So basically, we're just saying if there's nothing here that's less than 2, then we cannot hold water because we're basically on a surface, right? If the height of this would be 2 right here, imagine this is a dark square right here, a black square, then that's a surface. That's a flat surface we can store water. Now, if we find a minimum amount, a less height point in this lane, then we can store water in whatever the depth of that water is minus the height that's right here. So let's continue moving our pointer. Let's check our operation right now. We have right is standing at a height of 2 again. So we ask the same question. Hey, can we store any water here? Well, there's a wall to the left of height 2, and there's a wall to the right of height 2. Where I'm standing right now, it's equal to the height of my walls. So I must be at a flat point, right? I cannot store water at 2 if my walls are 2, right? I need talus walls surrounding me, and I need a minimum wall to know my water level. Like I said here, right? I need the minimum height because everything above that height would spill, and the actual height I'm standing right now. So let's try to use this little formula again. What is my minimum height? Well, my minimum height right now is 2. It's also my talus wall. What is my actual height? Well, it's 2. It's the point I'm standing right now. So again, like I said, there's no water to be stored here. It's a flat. I know that my wall under here is 2. I'm standing at 2. There's nothing I can contain there. Okay, great. So what do we do again? Well, let's go ahead and hope that on our right side, we can find a larger wall or a taller wall or a gap, a point where we can store water. We move our right pointer one more time, and look what we found. We found a talus wall of height 3. Now we update this as our talus wall. Cool, okay, so see what happens here now. We have a height 3 here, and we have a height 2 to the left. Can we store any water at this point? Well, no, because the minimum height is 2 using this formula, and the actual height is 3. So that's a negative number. We don't store. If we cannot trap water, we're not trying to subtract water from our water level, from our actual water level right here. We're trying to add, right? We want to know how much water can be trapped, okay? So this wall right here is not really subtracting water from us. It's just not a point where we can trap water in. So we don't add it to the answer, okay? It doesn't count towards our water. But we do count that that's a taller wall. And we can make an assumption and say, well, that's a taller wall than to our left. Should we check if there's any gaps in our left now? Right? We want to find either a talus wall on our left, or we want to find any gaps that are lower than 2, because that's the amount of water we can trap. Great. So now we move our left pointer. So left pointer goes right here. And as we can see here, we found a height of 1. Great, we found a wall of height of 1. We know there's a wall all the way to the right that's height of 3. But we also know there's a talus wall on our left that's height 2. So let's use your formula. What is the minimum height? Well, the minimum height is 2. It's this wall right here we found earlier. And the actual height is 1. Great. So that means we can store 1 unit of water above us because it would be contained between the height of 3 and the height of 2. So everything in between would be contained. We know that. And we just found a great point to start storing water, okay? So cool. We add 1 more unit of water to our count. And we say, hey, can we keep looking on the left since we found a height of 1, right? Still the higher wall. So let's keep looking. Well, we find a height of 0. Okay, we move our left pointer and now our height is 0. Again, we ask the same question. The wall towards our left, the tallest wall towards our left is 2. To our right is 3. And we ask the same question. Well, what is our minimum height? Our minimum height is 2. Again, what is the actual height? Well, 0. 2 minus 0 equals 2. We know the wall on the right is containing 2. It's greater. Great. So now we know that this is a gap right here, and we can add 2 units. This looks like a 2, but it's really a 1. Let's fix that. And let's add a 2 here. Perfect. So this little formula right here is what's going to help us find the water level that as we iterate through. So, I mean, I think by now the example got too extended. I think we understand that now. Let's go ahead and see that in code, right? So, like we said, we're going to use a 2-pointer approach. So we're going to start that at left and right. It's going to start in opposite ends. So left is equal to 0 and right is going to be equal to the length of height minus 1. Like we saw in the example, we need to know what is the tallest wall in our left and what is the tallest wall in our right. For right now, they're both equal to 0 because we know, like we said here, there's nothing to the left of left, there's nothing to the right of right. Great. And the next thing we need to save or track is how many units of water, right? We're going to call that answer, started at 0, we haven't started that yet. Traditional 2-pointer approach, we're going to try to check every possible integer in our array inwards, right? So we want the 2 pointers to be separate from each other until they meet. For that, we do until left is less than right. And then we check, well, what do we want to know now? Let's see if the wall at the left is smaller than the wall at the right. Why is that? Well, like we said earlier, the smaller wall is going to limit how much water we can trap because nothing above that would be contained. It would spill, right? So if I have, like I said, if I have a height 3 right here and I have a height 2 right here, I cannot contain 3 units of water. It would spill over. A unit of water would spill over until it goes down to the level. Perfect. So that's what we're trying to track here. Which height is going to be the limiting factor? And that's the height we're going to work with. Well, in this case, we're going to just track left and say, you know, if that's the case, it would be nice if I add my if statement. So in this case here, we're going to say, hey, if that's the case, let's first see what is the tallest wall we have seen. Remember, the tallest wall is the information we need to know at that point how much water we can trap. Because as we are scanning inwards, we don't know what's in between, but we want to know what we left behind, and that's the tallest points we've seen so far. So far the points are at 0. We haven't seen any tallest lines behind us. So we're just gonna say if the height at left is greater than the tallest wall we've seen, then go ahead and save that talus wall as our higher point, right? That's a way for us to update this. Now, if that's not the case, if we do that, we need to move the pointer, right? We need to say, hey, we found a talus wall. For instance, in this example right here, when left is equal to 2 and right it's equal to 1, we say, hey, we found a talus wall. Let's move the pointer to the right to find a smaller wall. So again, like moving the pointers when using a while loop, it's another good thing to keep in mind for when working with conditions. Now, if that's not the case, if we didn't find a taller wall, then let's go ahead and calculate how much water it's trapped in our point, because this question is this first statement here is just checking which one is the smaller wall. And the smaller wall is going to limit the amount of water we can trap. This statement right here is checking if the point we're standing right now is greater than the tallest wall we've seen before. Because if it is, then we cannot trap water because we're at a taller surface. If it's equal, then it's a flat surface. But if it's less than that, then we can trap water in it. At this point, we want to just check if it's the tallest wall. Did we find a tallest point? Well, if we don't, then that means we're on a gap. So we need to update our answer and add that water level. Remember that water level is going to be equal, like in this case right here. We have a wall of 2 here, and we probably have a wall of 2 here, but we're standing at height 1. So we can contain 2 units of water minus the height of the wall we're standing right now, okay? So that's going to be equal to the tallest wall we've seen, which is in this case 2, right? It's going to determine, hey, that's how much water we can trap. Okay, so left, since we're exploring left, right? This loop right here filters right here. If it's the left side, we need to track, okay? We'll do the right side iteration. But hey, what is the height of our tallest wall? Well, it's going to be equal to 2 minus the height of our actual point. If our actual point is height 2, meaning is equal to the height of the tallest wall, there's a flat surface. We want that to be minus or be under the height, so we can save that in our answer array. So what is that? That is the height of the point we're standing right now. Great. And then after that, since we finished an operation there, we move our pointer to 1 point to the left. Great. So what is the next condition? Well, if the left wall is not smaller than the right wall, that means then the right wall is the smaller one. So we just do else. And basically this mirrors itself right here. Well, we want to know if we found a taller wall in our right, okay? So if the statement, if the height at right is greater than the left, the right wall, or max, then go ahead and save that there, right? Because that's our tallest wall. And we update our right pointer. Remember, we're looking inwards, so minus equal. Now, if we didn't find a taller wall, that means we have either a flat surface or a gap, and that's what we want, to update our answer with the difference. So right max, our tallest wall, another point here, this is our tallest wall in the smaller area, the limiting area. Here we check if the minimum wall, what is the smaller wall of the 2 at that point? And here we're saying, well, the tallest wall I saw can contain as much water as the height of the point I'm standing right now. So that wall I saw was height 2 and I'm standing at 0. I can fill up all the way to 2 because that's the smaller wall of the tallest one I've seen. Hope that makes sense. So right max minus the height at my right point right now. And that's pretty much the algorithm. I mean, at this point we can return answer and we'll go through it. 2-pointer approach starting from opposite ends, or tallest walls we've seen from both ends. Because again, we cannot know what's happening in between them, but we know what happened at the points we already check. So we want to save the tallest wall we've seen, and the smaller wall of those tallest one would limit the amount of water we can get. Start our iteration here. We check which wall is the smaller one. If it's the left one, let's go ahead and check if that's the tallest one we've seen so far. If it is, save it, move a point. If it's not, that means then there's no flat surface or there's no a taller wall. So let's go ahead and save that difference, because that must be the water level. The tallest wall we've seen minus the height we're standing right now. After that, we move our pointer because we already checked that position. If the tallest wall is the left one, meaning the height of the right point is smaller, then we mirror that iteration and we say, hey, is that the tallest wall we've seen on the right? If it is, update it and move to your pointer. If it's not, then save it, right? And I'm missing something right here. I'm glad I look. We need to move our pointer again because we already operated on that point. And then we return our answer. I'm gonna give it a dry run so we can see that's correct. And again, there's easier ways to do this, shorter ways, like you can just call functions. But honestly, this saves function overheads, and you know, you're gonna get 97%. You're gonna be down here for sure, because you're not calling max on all this and whatnot. And this is an easier way to understand that. So yeah, that's how I solved the trapping rainwater problem. And yep, I'll see you in the next one. Thanks.